everybody's getting out your notes. And we're turning to page 16. All right, let's go. Notes. Let's go. 16, page 16. And you will recall that we had already discussed. We already discussed problem 5, A and B, but we gotta get to C. So, what we need to do is start, let's review how we did 5, A and B. So what did we start with? Well, we started with, we gotta know if we're going to store P or Q. And we had a 70% at P, which meant a 30% at Q, right?
Right.
If you weren't here when we did this, I don't know how many days ago, start thinking about it. It's exactly what we've been talking about. Then we are going to buy bananas, and the bananas are either delicious or not delicious. This is A. We're doing A. Or actually, we're just setting up the problem. So 90% are delicious from P, and 80% are delicious from Q. So then we said, find the probability that a random banana is delicious. So we multiplied this branch and got 0.63. And we multiplied this branch, the delicious branches, and we got 0.24. And then we added them together.
That's unacceptable. They're supposed to be a good.
All right, I'm going to start writing intentions for these. You guys got to get these taken care of. All this stuff that's just piling up. Actually, you owe me Kleenex for forever. Solomon, you too. You gotta get that taken care of. All right. So we added those together and said the probability of getting a delicious banana, and I'm going to use my notation, the probability of getting a delicious banana is 0.87. Right? I added these together. We know how to do that. I hope you know how to do it because you took a quiz over it. Now, this next one is tricky because the next one says, if I pick a delicious banana, what is the probability that I got it from Q? This is tricky, okay? This might be a bonus question sometime. Here's the deal. First of all, it's a probability question, so I know it's going to be a fraction, right? The numerator in any probability problem is what you want, okay? So what I want is to get a delicious banana that came from Q. That is right here. Aren't these the delicious bananas that came from Q? So the numerator is going to be 0.24. Those are the delicious bananas that came from Q. That's what I want. Now here's the tricky part. The denominator is the total delicious because it says in the problem, given that you got a delicious banana. All right? So we're starting at that place. The banana you got is delicious. Well, the total probability of being delicious is 0.87. So that's the answer to the question. In notation-wise, what this says is the probability of Q and delicious over the total probability of delicious. So when you read the problem and we talk through it, it doesn't seem like it's hard at all, but it gets confusing if you don't really slow down and read it carefully. So the question again was, if I pick a delicious banana, what's the probability it came from Q? So pretend I'm standing here with a delicious banana. It either came from P or Q, right? But it's delicious. So the total probability of being delicious is 0.87. The The delicious ones from Q are just this branch, which is 0.24. Huh? Got it? Okay, it's extra. All right. Now, C, everybody should know how to do. If I buy 2,000 bananas, how many can I expect to be not delicious? Okay, now wait a second. What was this? That's delicious. I want the probability of not delicious. Can you tell me what that would be? 0.13, that's exactly right. 13% of the bananas are not delicious. Okay? Everybody agree with that? 13% are not delicious. I'm going to buy 2,000 bananas. How many of them won't be delicious? What am I going to do? I'm not going to divide. I'm going to multiply 2,000 times 0.13. And that's going to give me 260 bananas. That's a hard word to write. Bananas. Okay? Once again, this goes back to something we talked about at the very beginning. If we want an expected number, if we're going to make a prediction, we take the probability of it happening times the number of, well, not the number of outcomes, but the number of events that we're doing here, possibilities. So there's 2,000 possibilities, right, to buy a banana. I got 2,000 chances. 13% of them are bad. That's 260. Okay? Now, the next one can be done easily and it can be done more difficult. So let's talk about this for a minute. A class contains 10 boys and 12 girls. We're going to randomly select 4. So we're going to reach in and grab 4 kids out of this class. What's the probability of at least one boy being chosen? Now, first of all, we could draw a tree diagram. But it would be a big tree diagram because we're choosing 4 kids. So it's going to have a lot of sprites coming off of it. Here's what I'd like you to think about for a second. What does at least one boy even mean? We're choosing 4. So at least one boy means 1 boy, and that would be 3 girls then. So 1 boy and 3 girls. 2 boys, 2 girls. 3 boys, 1 girl, or all 4 boys, right? Yeah, would you agree with that?
Yeah.
Okay. Oops, I just erased one. Now, let's talk about that for a second. This is a lot. So instead of doing each of these problems and then, oh, by the way, adding them together, because you could get 1 boy or 2 boys or 3 boys or 4 boys, and or means add. Instead of doing that, it's a big problem. What if I found the probability of no boys? Isn't that the opposite of at least one?
Yes.
And so, if I could find the probability of no boys, that's only 1 problem instead of 1, 2, 3, 4 problems. That's only 1. Well, let's do that, and then we'll talk about what we're going to do with it after we get it. Just think about that tree diagram. Now, the first branch of the tree diagram, you're going to get a girl or a boy, right? I want to get no boys. So I'm going to come up here. I'm going to lower this a little bit. So there's my first one. But I'm not even gonna look down here because I want no boys. So then I'm gonna have a girl or a boy again, right? But I don't want that one, so I'm gonna go here, girl and boy, and girl and boy. So would you agree that it's only this branch right here that I'm interested in? I don't need to draw the whole tree diagram. I just want that one. All right, now, let's put the probabilities on there. 10 boys and 12 girls in the class.
Yes.
So I'm gonna reach into the class of kids, and I'm gonna pull out a girl. What's the probability I'll get a girl? 12 out of 22, perfect. 12 girls, 22 kids. 12 out of 22. Now, I've got my girl, and I put her here. Now I'm gonna reach in and grab another one. What's that probability going to be? 11 out of 21. Why is it 11 out of 21? Because I took a girl out. Now there's only 11 left out of 21 kids, right? So now I'm gonna reach in and grab another one. So this is gonna be 10 out of 20. And the last one is going to be 9 out of 19. Now, here's what I'm trying to show you. Sometimes you don't need the whole diagram. If you think about the problem, if I did this, I would need the whole thing. But because I'm kind of thinking backwards, wait a minute. The opposite of at least one is none. And none is easy, right up there. Girl, 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 girl. Now, what do I do with those 4 fractions? I want a girl, and a girl, and a girl, and a girl. What do I do with them? Multiply them. This is a multiply problem. Remember, on the branch is always multiply. If I had more branches that I were doing, then I would add those. But on a branch is this and this and this, multiply. So you just take 12 divided by 22 times 11 divided by 21 times 10 divided by 20 times 9 divided by 19. 0.0677. Confirmation? Okay. Now, stop. That, my friends, is the probability of no boys. That isn't what I wanted. I wanted the opposite of that, right? So how do I get the opposite of it? Subtract it from 1. That's exactly right. You're either going to get no boys or you're going to get some boys. This is some. That's none. So I'll take 1 minus that to get the answer to the question. So the answer to the question is 0.9323. Did I subtract right? Yes. So the chance of getting at least 1 boy is 93.23%.
Well, it was the one that you add on, you subtract or add it.
What now?
And how do you need the 0.93?
That is the answer. I'm done. I'm not doing anything to
Right,
it.
but the 0.6, you say you add a 1, subtract 1.
Well, what did I do? Did I add 1 to that? Well, what would happen if I added 1 to 0.06? Okay, is that what I got?
No.
No.
Is it always going to be 1?
The total probability of every problem is 1. I mean, that's it, 100%. You can't have more than 100%. So what we're saying is 6%, I'm rounding off, 6% has no boys. Okay, no boys. So that means the other 93% or 94% has some boys. And that's what the question was. So
he's asking how you got from like the
I
point.
just told him.
Okay.
So we just did a problem then where we went in kind of through the back door. Instead of finding what the problem actually said, we found the opposite of it and subtracted from 1. This is always going to be easier when you have all of one thing or none of one thing. That's always easier than having these wacky combinations. Okay? Right? Okay. All right, now, we're not going to even start this next stuff because I need to give you a little bit of information to be ready for it. We're getting ready to start our card problems there. And so here's what I need for you to write down. We aren't done. This is important. Yeah, but it's separate. Yeah, I'm not going to start the problems yet. I'm giving you some extra information. So you can either write this down, like in the margin here, or you can get out a separate sheet of paper. We're going to do every one of those problems. Don't worry. But before we do, we need to talk about a mathematical concept called a combination. A combination is what happens when we choose items without worrying about the order. When I choose items from a group without worrying about order. It's something different when I worry about order, but all our problems in this section are no order, so we're going to do combinations. There are 2 ways that this can be written. Sometimes it's written like this, for example, and sometimes it's written like this. You need to be comfortable with both, because it totally is going to depend on the teacher you have and the book you're using. It's both ways. The way we read this is the number of ways we can choose 2 things from 8. All right? So we have 8 things, and we're going to choose 2 of them, and the order doesn't matter. Okay? So imagine that there's, 8 blocks on the table, and I tell you to pick 2 of them. That's written 8C2 or C82 like this. Okay? So the first number tells you how many things you have, and the second number tells you how many things you are choosing. In card problems, we very often see 52C5 because there are 52 cards and a lot of games use 5-card hands, right? So 52 cards choosing 5 at a time. Get your calculators out. I need everybody, turn it on. We're not leaving until we get this done. Turn it on. Press 8. I'm just going to do this problem. So press 8. 8. Then press your math button, and we've been using that. Click across the top row till you get to PRB, which stands for guess what? Probability. And then look at option 3. Do you see NCR? Press it. And then type 2. And then type equals. And the answer is 28. Okay? Now, one more. Let's do this one. How many 5-card hands in a deck? Here we go. 52. Math. Click all the way across. Down. Enter. And I messed it up. Did you get 2,598,960? All right, now guys, stop a minute. This is the total number of different 5-card hands there are in a standard deck. So when you start betting and gambling, remember, this is how many 5-card hands there are in a deck, right? Okay, I will see you on Monday. Kennedy?
Yeah, I will.
You better have a good